Hello, everyone. So, quick introduction. My name is Ahmed Faheem. I'm an associate professor at Temple University on sabbatical this year here at the AUC. And this is not my presentation. Most of this work was done with Konstantin Sobolev and his group, but it's on asphalt. So he felt like betraying his industry if he speaks asphalt in front of the world. So asked me to do the presentation for him. I was in collaboration with his group on this one and my other presentation in the afternoon after lunch. And I'll do my best to be very quick today because I know I'm the last one before lunch. So I'm sure everybody's looking at the clock. We're getting hungry, right? Thanks for your honesty. So this presentation is about the use of active cement or cement as active powder mix design. Let's put it that way. So in other words, we're trying to marry asphalt and concrete together to get us the benefit of both in our pavements. The idea of any pavement related research is getting rid of the distresses, right? That's what we always try to get rid of. And at the same time, improve or open new doors for new materials, new research ideas and projects for our PhD students. So this was a PhD study for Dr. Konstantin's student. Oh, I forgot to introduce the folks in there. So Behruz is the graduate student who made most of this work. This was a part of his PhD defense. Milad, Steve, and Clayton helped Behruz a lot, and Konstantin advised Behruz. And then that's me. So the hypothesis here is that we can work the benefits of the asphalt and the benefits of cement together in concrete. We have some challenges in doing that, so we had to think about these challenges as we designed the experimental program. The biggest challenge is that as you introduce particulates inside the asphalt in a viscoelastic medium in general, you will notice that the stiffness of your mix or your blend will consistent or continuously increase in this manner. So within what we call the diluted range, you still have enough medium in that for these particulates to move without really causing significant interaction, significant chemical or physical interaction on the binder. But beyond a certain limit, it's not necessarily this number, this is just for illustration, you get to what we call the concentrated zone, where you start having the particulate with the influenced binder around it, starting to collide together, and you're losing the flexibility and the flow of your bond. So if we are going to introduce or replace some of the asphalt with cement particulates, first of all, it has to be within a range that is feasible, like economically feasible. If it's 5%, if it's even 10%, it will be treated like a filler. So there isn't really an advantage of doing that. You're basically dumping a very expensive product into asphalt, as long as you are within this range, because the behavior will be influenced by asphalt for the most part. So we have to be somewhere close to that concentrated range. So the challenge would be that the stiffness, which is the y-axis, could increase significantly, and that's not helpful in asphalt because of workability reasons, because of susceptibility to cracking and so on. The x-axis here is the volume concentration, not by mass. So if in this study we were looking at this 40%, because this is based on a previous study that all particulates in asphalt reach the concentrated zone at the 40%. So that is the introduction to the story. What we observed that, or hope to observe, that these particulates, in addition to binding benefits of cement, could help in resisting cracking, whether it's through crack pinning, through rechanneling, and we'll see. I know what the result, but I'm not going to share it yet. Show it at the very end. This is from a study on another active powder, which was fly ash. And we noticed in our studies that these kinds of behaviors, as you can see, the crack ended at at the interface with the particulate. So we'll see if this translates into true mechanical behavior, improvement in the mechanical behavior of the mixtures. In doing so, we had to select our materials carefully. We wanted to use an asphalt that is representative of the market, and also modify it with different modifications so it's more encompassing the entire market. We wanted to get to a volume concentration that is really economically feasible, really mechanically also beneficial if we get there. And as we are building our concrete mixes, we build them to a certain compaction level. So we have to maintain a certain level of air voids within the cement mixes. So the binder we used was a typical PG 5828, typical for Wisconsin. And then we modified it or added some additives to it. So like adding a polymer, that's considered a modification, represented by the plus P, added a warm mix additives, so that will help it be more flowable, more lubricant. That's the plus W, or the combination of both the warm mix additive and the polymer modification. Then for these different combinations of binder, we blended that with cement at different concentrations at the mastic level, which is just the binder and the powder, to investigate at that level what's going on. Is it feasible to move to the mixture level at the target concentration or not? Also, we wanted to have a control to compare the behavior against, which in our case here, it's just a limestone, which was proven to be inert when interacts with asphalt, against our Portland cement. And of course, getting the specific gravity is important for us to calculate the volume fraction. This presentation was a part of a very comprehensive study, but for the purpose of this workshop, we did select some of the results to include in our study. So for example, this is for the mixture side too. So for example, we wanted to look at viscosity. Now, as you can see, the trend of the viscosity versus the concentration of whether it's Portland cement concrete or the limestone, the increase, like in the very first slide, the increase in viscosity is also taking the same shape as a function of the concentration. Whether it's a typical binder, whether it's the binder with the warm mix, or the binder with the polymer modified, or the binder with both warm mix and polymer modification. The trend of increased stiffness, increased viscosity is observed. So that raises a little bit of a flag. That could be an issue with workability. We'll see when we get to the mixture side. We also looked at the complex shear modulus as an indicator also of stiffness beyond construction. So viscosity helps us understand constructability. Stiffness helps us understand its behavior in service. Again, the same trend was observed. What we plotting here, the y-axis is the relative stiffness or relative G star, not the actual value. So all these values are divided by the control without any additive. So that's why we start from 1 and we increase. So basically at 25% by volume of these additives, our stiffness increased maximum of 3-fold and minimum of 2.25, something like that. And the interesting part is that whether you are using a lubricant, the warm mix additive or not, whether you're using polymer modification or not, does not really affect the ranking. It's all over the place. So all of this is not really damage dependent. This is just understanding the basics of rheology. We wanted to also characterize the final product in terms of its damage resistance. So we applied a damage controlled or damage influenced test called the massacre test, multiple stress creep and recovery, where you expose the material to cycles of creep and rest to see the level of recovery of the deformation, and then separate the results into what is permanent deformation or damage and what's recoverable deformation. This test is done at high temperature, which is a good indicator of the behavior of this material in the summertime. The results are showing that the non-recoverable compliance so basically a measure of the damage, drops significantly as we add these particulates. But it does not distinguish between cement or limestone. So adding any particulate increases the stiffness, decreases the formation, and in return decreases permanent damage. So you can see that limestone and Portland cement are getting us almost similar results. And it doesn't matter what kind of binder combination you're getting, but we're seeing improvement. However, when we get to the recovery, the expectation is when you are working with non-polymer modification binder, you don't have recovery. At this high temperature, most of the deformation is permanent. And you can see that for the base binder, you only got 1% recovery, which could be related to inertia to begin with. But as we added the particulates, the recovery increased slightly, but 3% is also not observed. Is not that significant or that of an important value from the point of view of rutting resistance, resisting permanent deformation under the tires. But once you flip to the polymer modification, you'll notice that the polymer inside the binder is what's in control of the recovery, not the particulates. So we start with almost 50% recovery of the observed deformation. And we kind of maintain the same range, somewhere between 50 and 30, which is acceptable range. But the interaction with the particulates show some mixed results, some drop when you are talking about the the regular binder just with modified, but you don't lose that recovery when you add the warm mix. So the interaction between the modification and the particulates is really very complex, and you will see that trend all over.
لبس كده بحب اللبس ده، لابسه تيشيرت بلوزه تحت وبتاع كده اصفر.
Can you mute yourself, please? Okay. So we wanted to look at another test using the dynamic mechanical analysis or analyzer. And in this test, we applied at very low temperature, minus 18 degrees, multiple cycles of loading with a ramp increase in force. From that test, just a second. We calculated the creep compliance, and we are also seeing mixed results from the test. We are seeing no serious difference between the limestone and the cement. So still, at this moment, we're still not sure if the cement actually beneficial or not. Looking at the relaxation, we are seeing for the warm mix additive, it drops the relaxation of the binder significantly, which is counterintuitive if you didn't see the results. However, the binder recovers that ability to relax as the particulates increase. So that interaction or increased stiffness, or I don't really know what yet because we didn't look into it, seems to negate the bad effect of the warm mix. Once you get into the polymer region, whether you use warm mix or not does not affect your relaxation. Again, because the polymer here is the dominant phase in achieving that relaxation. And as we saw at high temperature with the multiple stress creep and recovery, we are seeing that the particulates influence that ability again. So since we don't have a verdict yet, we thought let's go to the final product and build a mixture. And the challenges here will be even bigger, because if you look at the produced mixes, in order for us to use cement, we have to drop the asphalt content significantly. So the control mix had a 6% asphalt, which is a typical mix in Wisconsin, and we almost dropped by not almost, it dropped by 40% due to the presence of cement. What's the problem with that? Cement might be working as a binder or not, we don't know. The problem is here, that the film thickness of the asphalt now is way thinner. The total volume of the binder is expected to be the same if you combine cement and asphalt. but we don't know if the cement is active in the mix or not. So the film thickness that is controlling really everything about the asphalt mixtures is dropped significantly. And this is calculated based on binder only. So how would that affect the mechanical behavior of the mixture overall? So we looked at multiple tests, moisture damage and fatigue specifically, again, because they are damage related tests. If you look at the moisture damage, the passing, we calculate something, the tensile strength ratio, which a ratio between the tensile strength of a conditioned sample in water, so exposed to moisture damage, versus the tensile strength of an unconditioned sample that was not exposed to moisture damage. And for these mixes with warm mix asphalt, again, with limestone and Portland cement, they are all passing. However, what is not shown here, and I couldn't get the results in time, the strength values that we are dividing over each other for the Portland cement was much higher, way higher. So the conditioned samples strength is way higher than the unconditioned strength of samples without cement. And it makes sense because, you know, you're adding cement into moisture, so the hydration starts. This is the exposure to moisture, it takes a long time. And once you move to the polymer modification, you almost don't see any moisture damage. The tensile strength ratio is 98%, so it didn't lose anything of its tensile strength, which is critical in resisting stripping and also an indicator of crack resistance. So what we saw at the binder phase, which was giving us mixed results, seems to be showing the opposite at the mixture level at even higher concentration. And if you look at the fatigue testing, this is a cyclic loading in direct tension also. So we are really stressing the weakest phase in the mix, which is the binder. And as you look at the limestone versus the Portland cement, you're talking about almost more than doubling the service life or the number of cycles to failure in the presence of cement with unmodified binders. Once you go to the modified binders, the same behavior takes place. So warm mix binders with polymer modification, it seems that the dominant contributor to fatigue resistance or crack in resistance, in our case here, is the cement, not the polymer, unlike what we saw at the binder level, which could be translated into many different or stipulated, maybe because that's an increase in the aggregate to binder, there's an increase to binder adhesion or increased cohesion in the binder phase because of the cement. We didn't really go that deep yet, at least in this study. And if you look at the actual amount of deformation at failure, again, the cement mixes completely outperforms, like a very different mix design altogether, very different binder or aggregate structure. So we're talking about improvement, significant improvement beyond what we could capture at the binder level. And that's really the danger of focusing at the binder level with certain additives, specifically active powder, and thinking this is the determinant parameter. But once you get to the mixture, the dynamics of the failure, the stress distribution is very different. Even the dynamics of the applied tests are not exactly the same. They are very different than the binder testing, which is more rheology based and less damage based. So why do we think this is happening? And I think we found the results in these pictures. If you look at the limestone and the cement pictures, you'll notice that some of the, looking at the cracks that are created, this is done at liquid nitrogen, almost negative 195 degrees, that the cracks are getting filled with the products of hydration. So in part could be not only that increased in adhesion and all the stipulations I was just talking about, but there is a healing component there that must be investigated and accounted for as you're characterizing this product. And also as you're planning, new specs and new manuals for implementation. so you don't do it wrong and people miss the benefit. And healing has been a ghost that we've been chasing for a very long time and unable to achieve with the asphalt alone. A lot of additives have been added to it and fiber, so many things have been tried, but really couldn't achieve that level of healing with this clarity. Limestone, crack unfilled, type 1 cement and CSA. So I think the really improvements that we have been seeing at the mixture level, to a great extent, from my little bit of knowledge in cement, is attributed to improvement in the contact between the asphalt binder and the aggregate, and the self-healing that is taking place. So I try to be as quick as possible to get us to lunch. And just to summarize what we're talking about, really what I wanted to highlight, not that the cement is the greatest thing in the world or anything, because then I cannot betray my industry, right? But really characterizing complex materials like that cannot be done with traditional means, in my opinion. We have to really dig a little bit deeper in order for us to understand and capitalize on the benefits that we can achieve with this kind of approach. Thank you for your attention, and thank you for all the supporters of this study. And with that, I let you go for lunch.
Thank you.
Unless you have questions.
Still, we have time for a few questions. Not you.
I think he wants to correct something I said.
Yes, maybe. I have one question. I was in my time at MIT, we were working with Ferrovial. Ferrovial is a Spanish company doing asphalt for highways, right? And the idea, you know, when you put asphalt, you need to be above TG, the glass transition temperature. So you have a thing flowing. And that temperature is typically 180 Celsius. This is bad news for cement, right? I think so. I mean, that's the thing. I mean, you cannot do that with cement. I mean, the cement paste. You can do that with grains. So how
if I understood your question correctly, as we are producing these mixes, the temperatures that for mixing and compaction was between 135 degrees for mixing and 115 degrees for
that's
compaction.
enough to do the bit.
To achieve the especially with warm mix additive. Yeah. That's in part why we wanted to have a low energy mix that is also self-healing. Hopefully down the road we can.
But the cement is not. Is that the cement paste?
Not paste.
The cement grain. Yeah. Powder. Because you will kill the cement paste, Because just tell you, we did some kind of image analysis. Yes, please. So this is the cement grains, the from the sack, the cement sack, right?
So it's a cement particulates.
Yeah.
Not paste. No, there's no moisture. We can.
No. So now I understand that the binding, because the binding with the asphalt thing for us typically will be very strong, because that's kind of temperature. You remove OH groups from the cement side, and that will bound like chemistry with asphalt. Now, because I tell you that what we do with Ferrovial, we did some like, that kind of sample, we crushed them. And I was expecting the cement not to bind, the asphalt not to bind to the grain, not cement, grains. So we a black and white image, or black, everything would be asphalt on one side, other grains. No, actually the fracture went through the grains. So it was black and white, both sides of the image. So, and why is that? It's because the chemistry was very strong between the asphalt and the cement grain because of the temperature.
Oh.
All right. So I was very surprised to see the fracture going through the grains, because I was expecting a kind of debonding from the asphalt grains.
Yeah. Oh, thank you.
Where do you want me to go?
Finally, I got the mic. So thanks. First of all, Ahmed, thank you for excellent presentation. And he mentioned, like, in a very humble way, his contribution, but his contribution is really extremely high to all this experimental program at UWM related to asphalt, because it's actually a continuation of Ahmed's PhD, which he did like 15 years ago when we first met. And this collaboration, is ongoing collaboration. We have a few projects together all the time. And so his role in this project was really consulting, but he inspired us he helped us to set up the experimental program, which was extremely important for us. So thank you, Ahmed, for this. And thank you for taking charge today. So I like to mention—
Didn't have a choice.
Huh?
Didn't have a choice.
Yeah, okay, well, thank you. So I think what is important maybe to mention, again, it's like more like a comment that the quantities actually of asphalt binder were significant. So we used way smaller dosage of asphalt binder. And asphalt binder, if you look for cost, because like in construction business, like we discussed, cost is important. So it's $600 roughly per ton. I don't know, prices may inflate it like recently to maybe 25%.
Polymer modified
up.
is twice as expensive.
Twice now?
Twice as expensive compared to unmodified. So
Portland cement is still, I think, maybe 20% up, but again, the ratio was like 600 to 100 when we started this job before COVID, let's say 3 years ago. And now it's asphalt went up, and the shortage of asphalt was also something which we expected. And asphalt recovery is actually from oil is changing, so we have less different type of binders. So I would like to mention that this really technology helps us to save most expensive component on one side, and on another side is to replace with, yes, not cheap, not like limestone, and we compared in this specific work limestone, which was manufactured limestone powder, because common asphalt technology would include filter, but this is baghouse filter, which is uncontrolled powder mix, which is variable and gives variability to the mixtures, etc. So this is, I think, is the importance that we need to modify. I think asphalt is still the polymer material which is produced in huge quantities, but is not engineered at this mastic level, which is bitumen plus powder. And this needs more attention. And this is like what our joint work is, shows a great promise. Okay.
Thank you, Konstantin. Do we have questions online, maybe? No? Yes, please, here. Yeah.
This is very interesting approach to modify the bitumen. And it seems to be in the beginning that it's a physical effect, but when it's exposed to water, it became a chemical effect. Wouldn't that affect the brittleness of the asphalt at that point?
Down the road, I'm sure once the proof of concept is achieved, we'll have to apply aging and dynamic loading to mixtures to capture this effect. The idea from the hypothesis level is that the flexibility will be achieved by the binder, and the rigidity or the strength will be achieved by the cement. We could not really, to be very honest, capture that at the binder level only. We had to go to the mixture level to really see that effect. And we could see that from the fatigue repeated loading testing. The amount of deformation was significantly reduced, and the number of cycles to failure was orders of magnitude more. So to answer your question shortly, I think some of the results are indicating that this is not a concern, but again, we only tested one mixed design. So it cannot be conclusive at this level.
Okay, there is a problem in Egypt about the stripping of asphalt under effect of moisture. And up till now, we could not see a solution to that, including adding the cement. So is that because we added the cement to the mixture, not to the asphalt?
So I was going to ask you, how do they add the cement? Is it blended with the aggregate first and then the binder?
I think it is. That's the situation.
So most of the
your approach will say, if you blend the cement to the binder, that might solve the problem.
Or later in the mixtures, so the drum itself, if you introduce the aggregate with the cement, a lot of the cement will be either hidden inside the voids or conglomerated with the binder, so the effect will not be seen. as you are in the process, as you are moving down the mixing process, there is an area where you can introduce fines right before the binder. So as they are introduced, they are blended with, almost blended with the binder before the mix. I don't know if this is what they do or not, because blending the cement with the binder before introducing it into the drum is going to be a challenge from pumping point of view.
Oh, you mean the manufacturing process
For
itself?
the manufacturing process. So it
I-
can be tried later on within the mixing phase inside the drum. We've tried that before and we've seen better. What's?
Go with the mic.
You can take mine.
Thank you. So Ahmed is absolutely right. And initial concept was if we mix powders with bitumen, and this is the way we did when we produced mastic. So we would mix, we have mixers, we had protocols to mix. And so we have perfect mastic. So powders are incorporated. Yes, it's more viscose. And this was approach when we came to the scaling up to the industry. We said, well, they believe this is the way to go. You need to invest $100,000, $100,000 for the mixing, And they were resistant. They said, "What? We have a better solution." And mix the pumping is one, and they were really scared to destroy the pumping equipment, etc. Initially, they were excited because when we saw the results, they said, "Oh, we can just mix it in with bitumen, the powders, and we sell."
Because these powders
Modified
cheat the PG grading system. If it's
Yeah.
blended, if you add that cement or any powder really
Yeah.
to asphalt, it will increase its PG and it will pass. But
But
they started thinking like that at first.
But what they suggested, actually, they have this injection system somewhere in the middle of the drum. So when already coating is achieved, the powder is injected in the middle, and powder is incorporated inside of the already informed asphalt. And so powder is incorporated in this way, and it's not clogged, it's not covering the aggregates, etc. So this was tried, and it was very successful because companies already have systems to inject, for example, cement kill dust, which was used in the past also for anti-stripping. But now cement kill dust is not there anymore for some reason. And so they had systems so we can inject cement or a fly ash there.
Yeah, maybe cement is just not the right thing to use actually, because in the end, this is any powder. Any powder that's a large amount of chemistry at the surface. I don't know the density of OH groups at the surface of C2S or C3S, but maybe you have silica. You know, in silica, you can go from 3 to 13 OH groups per nanometer square. So if you were to use this higher end of silica, which I don't know where in the world you can find it, but there is, the thing, then you will have a super reactive powder and probably more than cement.
This started with fly ash at the beginning.
Yeah, of course, yes, yes.
So that's how we started, and this is a test section. We built a few test
fly
sections.
ash is in between. Fly ash is 5 to 6 OH groups nanometer square. So we are at the very beginning. If you were to optimize just for this kind of chemistry measurement, cement is just a bad thing in the end. You should maybe go for large OH groups containing silica, and that will be even more reactive.
We did
with asphalt at that
for the
temperature.
fly ash. I was just writing something today, and we realized that the silica content in the fly ash plays a big role. I just remember this now, but this is why we collaborate with Constantine, because that's not my area.
I think the measurement will be this density of OH group the surface, and that is typical for any oxides, silica in particular. And in case of silica, you have a wide span of possibilities, probably way more than C2S or C3S, the cement grain itself, which is a silica-based particle.
Only interaction of the powder and the bitumen is the role of cement is in self-healing at very late stage when asphalt already breaking or cracking because of the age, etc.
I guess you will have the same thing with silica.
Okay, well,
yes.
We can give it a try.
Yes, that's what I'm saying, because in this case, you're not using cement for its hydration property because of the temperature thing. It's really like binding with the asphalt, and maybe you're destroying, making the silica gel, not a gel, a glass, say, more glass that can flow into and cracking. No, not high temperature glass, but that's more like a gel. So that's maybe the kind of the real thing is really the chemistry again, to
Well,
the silica chemistry.